Okay, so I'm going to make a video to give you an example to help you if you want to do the bonus points project for MENG 383. So I picked two different problems. I think I'll make it into the same video. So if you want to skip ahead, this is going to be the kinematics demonstration. I picked an example out of class 16. Something you should consider, it's probably better to pick one that has a constant angular velocity as one of the inputs. It's a bit trickier to try to match up results with if you have angular acceleration in the parts, because then you have to try to figure out a way to start it in the right spot so that when it gets into the position that where we care about, so we can match up the results so that they'll match up. All right, so that's probably longer description than it's necessary, but just keep it to say that if you want to do the rigid body kinematics, it's probably better to pick one that has a constant velocity, angular velocity input. And now this one does. So this is a 5 radians per second, which turns out to be 47.75 RPM. And the dimensions, you see that they're 90 millimeters, and this one's 180 millimeters, and this is 242.3 and 242.3 right there. So, and then there's 225 in between. So what I did, I've already made this just to double check that I could, but I will pretend like I'm making it just to give you sort of pointers. So it started with a new part. I encourage you to pull this down and pick white as the background. It just makes the thing look better. Don't forget to change your units in the beginning to what you want. So this one we have millimeters, so let's stick with millimeters. And I'm going to go to the front plane and create a sketch. I like using this utility up here, that straight slot. And I'll dimension this part right here to being, what did I say, 90? Yep. And then I recommend you just try to use the proportions to make it look kind of reasonable. Here I think it looks like 10 millimeters is probably going to make that about right. And therefore I'm going to make the holes about 5 millimeters each. You can do any size you want, but I think these are reasonable sizes for proportions for what the thing will look like. And we'll extrude that so that it's already selected. So I'll extrude the thing out. And that looks a little thick to me, so I'm going to make this also 5 millimeters. Yeah, that looks about right. All right, so I encourage you to make the thing kind of colorful, so you could pick out, I'm sure there's bunches of different ways that you could do this, but here is how I'm doing it right there, just to pick the body and make it yellow. This one happens to be yellow. You can save it now, or even before you go there, we're going to go to evaluate on this and go to the mass properties. And we don't have to, actually, I'm sorry, this is a kinematics, so we don't need to do this, but if he was in kinetics, here's where you would override the mass of the thing right up here. You would set what that's equal to, but we don't need to do that. But I can actually show you from the results of this how you could pull out some kinetics results after the fact. But anyway, I encourage you to save it with a name that makes some kind of sense. Here I've named a bunch of parts after the examples. So I'm just going to pretend like we saved it. And something, so here I'll just name it part 5 right here for right now, lazily. So you might want to change this again. So like, don't have to recreate it all the way. This is just a suggestion. If you're going to make a bunch of different links, all right, come on, stop it. I got the little hand symbol there. There you go. I'm going to expand this down. Expand it down. Come on. It's mad because I have a bunch of things open. So we could go to the sketch. Oh, come on. Open up. I gotta be like that. Anyway, there you go. Go onto the sketch and say, because we want to make that other link, we could make it 180 right? That other link was like the rocker for the thing was 180, and you can. Okay, so what I should have done. Sorry, whoops, I made a mistake. Let me go undo. Nope, not that undo. Yeah, there you go. That's good. All right, and save it, and then you go like save again, like save as. This is just a hint. Don't know. Hit the save as a copy right here, and open. Save as a copy and open. That'll leave the other one open right there. I forgot to change the name, so go part 6 or something if you're a lazy person. Don't want to come up with the correct name. All right, and then you get this all the time, but say keep the original document open. It just makes it a little easier to have them all open at the same time. And now you can make that change. So this is the new link, and maybe this is the other piece. It's going to let me do it this time. Very hinky right now. There you go. And I could just change that to 180, and then just save it. All right. So you could do that with and it just helps to make a bunch of links if you're going to make something really quickly. Is to just change that one thing. It wasn't letting me change the color this way for whatever reason a little while ago. There you go. Let me do it this time. Okay. So it's nice to make them a bunch of different colors. All right. So anyway, I assume that you know how to make links. So let's go and make a new assembly. And in the same way, okay, so you could bring in that first part. I usually make a ground, right? So in this case, I made them green. I like green for ground. Made that part in here. One thing that you should know, make sure that you change this to your units right away in the assembly as well, because you get the output the same. And let's change the white background to white. See how much more vibrant it is. One thing you should know, the first part that you pull into an assembly always gets fixed. So you have to right click it and go down to float. It won't happen to any other parts when you bring it in, but you'll have a difficult time getting this thing into the orientation that you want. When I go to mates for a part, that initial part that I want to be the foundation of something, I find it's quite useful to use as the basis of the mates to grab them and match the planes with each other. So I mate the planes. So here's the plane for the part, and this is the top plane for this, but I would kind of like that to be matched with the right plane globally right here. And it'll do it here in a second. Boom. Okay. So I'm going to accept that because I wanted it horizontal. The front planes should be pretty much the same. Yep, they're the same orientation here. So I'm going to accept that with a little green check mark. And then I'm also going to have one more plane right here. I think it's the right plane needs to be with the top plane globally. Yeah, so it didn't have to move much to do that. So now the thing is completely constrained. I have got it all in there. And I'll accept it. Okay, and so let me get out of here. And now I'm going to input the other, not mates. I accidentally hit mate. I want to input the other parts. So I'm going to put in my crank. And I'll put in my rocker. And I will put in my coupler. And some of these things, obviously, you should probably already know if you're attempting to do something in SolidWorks, but I figured I would tell you about them because there's a couple things coming up with the mates that are going to be particular to using it with motion. So I first made those coincident to each other, and then I made them concentric right here. Do the same thing with the rocker. And then I'll make this concentric as well. And then lastly, let's do the coupler, back side of that. put it onto the front side of this. I'll get the coincident right here. Something I meant to tell you, I'm going to remember to tell you, when you're making one of the parts where things where you have a well, let's bring this. I'll mention it here in a second. I'll finish this up first. Okay. See, we get this close to being fully constrained, so you can see that we can make the mechanical motion that we anticipate that we want to. I'll talk about that in a second. Okay, so now I want to add in the initial positions, usually the last mate that I want to make. So I want to make this thing in 90-degree orientation right here, because that's the position. Whoops. Oh yeah, no, that's fine. It jumped into that position, but I can go back and click on this angle, and it's going to be close to where it originally started from right there. So I'm going to put in 90 right there and say OK. All right, so now I force that thing to be 90 degrees. I'm going to suppress that pretty soon, but that's set where the orientation for the beginning. So I'm done with my mates. Now what I was alluding to, let's get ahead. Before, and I kind of stumbled over. Make sure if you're going to want to have a point of interest, and let's say it's going to be right here, that you put something in there that you can track. I found that to be quite useful. So in this part, I put a sketch on top of this face, and that sketch, the reason I put it there was just to add a point onto it. So I'm going to use that as my reference later on. So that's what I noticed it and I wanted to mention. All right, so we're going to go to a motion study, a new motion study. I'll pull this thing up so you can see it a little better. And I'm going to move this out a little bit. Okay, so one of the very first things I would suggest that you do before anything else is come up to this orientation in camera views. And my machine is getting kind of slow right here. Let's see. You want to right click or left click? You want to left click. Right click and hit disable playback of view keys. That will save you a lot of aggravation, because otherwise it'll try to make the orientation always the initial orientation, and you want to try to like see it in a different way. Now the next thing to do is to make sure you have the add-in. Pull this down. If you only see basic animation of basic motion, you don't see a motion analysis, you need to come up and go to this gear up atop, go to the pull down next to it, and go to add-ins, and you need to have SolidWorks motion right there. SolidWorks motion. If you don't have that, if that's not available, you can't really do this project very effectively. You're not going to be able to pull out results. So I'm going to SolidWorks motion analysis, and now we have to make some decisions. Well, first off, okay, I can come down here, I can expand my mates and go to the very last mate, right click it and hit suppress. Right, and you might want to scroll back down, just double check it's grayed out. That's going to allow it to now move, because we're going to put a motor onto it. So we have to start making some decisions about how long the analysis should go for. I kind of like often to make 3 rotations, and I'm going to plan it out just a little bit. All right, so this guy is going to go at 47.75 RPM. So I'm going to go to calculator. Not that you need me to see this, but maybe okay, so wait a minute, let me come back to that. So let's see, I like a scientific. So 5 times pi, right, times 2, and then divided by 60. That didn't come out right. 5 No, I have to multiply by 60, right? Radians per second into RPM. Yeah, see, so I'm sorry. Okay, divide by, divide 5 by pi and divide by 2 and multiply by 60. There you go. 47.75 is pretty close to the thing. Now, I want to make it go 3 revolutions, right? So divide this by 60, again, right there. And here's revolutions per second. Let's make it go about 3 times. So that's going to take 2 minutes, 2 seconds, 2.3875, call it, seconds, right? So that's, I've decided that. Let's come back into here. So I'm going to drag this over to as close as I possibly can get to 2.875. All right, so that top diamond that I'm pulling in. And now I'm going to zoom in. And I'm going to keep zooming in so I can get it to 2.875. All right, I missed it. Where'd it go? Where'd you go? Oh, I moved too fast by it. Where'd it go? There you are. All right, so I can't see this very well. It's at 2 point. See, where is that? Right there. A little hover over it, and it's 2.82, 2.88, 2.87, 2.875. Is that what I said that I wanted? 2.3875. Oh, you do, dummy. All right, so some over, going to be over here just a little bit. Yeah, more over. Oops. Should scale this. All right, so where are we? 2.39. How much is it going to let me go? 2.386. 2.388. So zoom in. But, oh, come on. How did you manage to go that far over? There you go. 2.88, 2.3, $875, right? 2.3875. Yep. I can zoom out now. Okay. And when I come into my time steps, I went to 2.3875, right? And I tried to figure out, well, this looks like divisible by 5. So I said, A equals divisible by 5, divided by 5. And then I didn't do another divided by 5. Sure. All right. So I looked at that and I said, oh, 191. Let me make 191 time steps. I don't know if my logic worked out. It worked out for me later on. So I got the time steps to give me pretty even increments of things that I kind of liked, right? So you can fudge it yourself to whatever you want, but just maybe that kind of mindset that you pick a certain number of things, certain number of time that you're going to put onto the thing and see if you can match it up, right? So it's kind of an important aspect. Now, I'm going to put in a motor onto this thing. And so I've picked on the motor here, but you'll see that it's going counterclockwise. So I'm going to change the direction. You see now it's clockwise. And here is where I have my 47.75, right? Which is what that is, right? 47.75, sure. Okay, so by the way, things that I'm looking for in the solution of this, we were looking for the angular acceleration of this member and the acceleration of point E, right there, right? So we found 5 radians per second squared and 900 to the left. So that's really what we're trying to match up. So I think that one's good right there. And let's see if we've got everything working correctly. We should be able to hit this calculate button and have it come through for us. And it starts at 90. It should end pretty close to 90. Boom. That didn't end as close to 90 as I would hoped. Not in my previous attempt, so I don't know what I did necessarily wrong there. I'll play it again. Huh. All right, well, let's see. We can open up the other one and see what I did correctly, but I got a better, closer to 90 from my choices. I'm not sure about my 191. So let's pull out the results. This is like one of the important things here. We get the displacement, velocity, and acceleration. I like to do the trace path first. So I just like to see the trace path. So what I'm zooming in, that's where I'm picking that point right there. And so you zoom out, you can see that's the path of this one. Not all of the problems that you'll try to do have this kind of cool, we call this a coupler curve, but it's kind of a neat thing. And now let's see, get my, a good thing to start with, right? If you want to try to match things up is to have some kind of reference. So a good starting point is the angular displacement right here. So I'm a displacement velocity analysis and go to angular displacement and pick this guy. And magnitude is, by the way, is the only drop down that you have right here. So we're going to have that right there, which makes sense, right? Because it's that it's going to be a slope coming this way, and it negative is clockwise. So you can see that it's coming downwards right there, and then repeats, and it goes. You'll see it goes to negative 180 to 180. My font is really small on this because I'm just some graphic cards issue. But this is a good first thing to use because it's going to be our reference for the other graphs that we're going to do. So we'll go back to this output thing, and let's take a look at. I don't need everything under the sun. But it might be interesting to find the velocity at that point. It might be interesting and other things. But let me just find the acceleration because that's one of the things that we wanted to try to get. And I'll do the X component first and pick that spot. An interesting thing to do is to turn on the little vector thing onto here. But before you go on, let's add that to the existing plot. So we're going to add that to the same plot. It's going to help us because we're going to export them all at the same time to Excel so we could take a look at the numbers. So we'll add that on there. So there's what the acceleration looks like. And you can also see the vector. I think the vector will show up now when we play. Nope, didn't do it. It made me a liar. Something that you should be cautious of, though, and this is a weird bug, is the first time that you add, or sometimes when you add a plot to this existing plot, for whatever reason, the range is incorrect. And the way to fix that is to go and expand the results down here, expand this, right-click on it, and just edit it. And I usually just pull this down, pull that back down. And you saw that it looks like it's like negative 10 to 8, but that's not correct. If you do it again, oh, now it shows at negative 10 to 8. Okay, it made me a liar. So, but just be aware that sometimes that's something that you have to do to try to fix this like little bug that's in this output. I'm going to do the Y, that should have been the X direction. Okay, that may have been. I'm going to put the Y direction too, just out of curiosity. It should be 0. That's what we're looking for it to be. We expect it to be because it's, according to the problem, it's all in the X direction. But I'll put this in as a check. And we'll add to that existing plot again, plot 2, and put him in there. All right. And let's see. We still don't get that arrow. I wanted to see the arrow. I'm gonna hit calculate again. Let's see if the arrow will show up now when we go to the playback. Is the playback gonna give me an arrow? No, why? I want to see the arrow. I'm gonna come back and edit this. Make sure I clicked it. Oh, I didn't. There you go. Click it. There you go. Let's show vector in the graphics window. Is it gonna show it? There you go. See, it's a cool looking thing, right? And change it to make it go a little slower, so you can see the arrow. Wee. See, that's kind of cool, isn't it? All right, so that was worth it. We also want to compare our angular acceleration to the piece. So let me add that one on there too, and then we can see what the results look like. So here we go, category angular acceleration. I could do the angular velocity too if you wanted. Let's do the angular velocity. Let's do the angular velocity and angular acceleration. So I'm going to pick the Z component right here because its Z is coming out of the page the way I have it arranged. And I think I just have to click that and I'll add it to this plot. Plot's getting pretty crowded. And one more. And let's see, angular acceleration, do the Z component, pick that part, and one more, add it to this plot. Once again, I had said earlier on, but be mindful that if you get wrong results, you might want to come back and double check. What you can do is just go to this. If you do get wrong results, one thing it could have been is this little bug. You just have to come back into this, do it once, and it'll change what the range looks like right there for some reason. But now we can open this up, export it to a spreadsheet. It'll take a little time. I already did another one, but you look down for Excel will open up eventually. And there you go. This one. This is the one that's shown for this particular thing. So like, all right, I have my angular displacement right here. It was the first one that I picked, and I'm gonna pick. I'm gonna change the number so I could I don't like the scientific notation. Let's make it there. That didn't come out the way I expected it to. Let's see, here's a previous one that I did, and I got the angular, where's the angular one? Angular displacement was right here. Yeah, and it was counting down. See, it was doing for a reference coordinate system. So I did something differently this time. I got to see what it is. I think it might have been, let's take a look at our time increment. My time increment goes 5, 10, 16, you know, but let's see, did I have the same one here? Yeah, it's the same time increment. So, but anyway, the angular increments look like they were actually pretty damn good when I did this before. So I don't know why it would have such a different one. But what I'm really looking for, is it's not going to be very good results on this first one where we started. So I'd like to see it again, 90 degrees out. Or not 90 degrees, one full rotation. So we wanted to see when it gets to 0. I guess because this one started at 0. This one's starting at 0, so I guess we want to see where 0 is again. So it's going to go all the way down. There you go. So we want to get to 0, and it doesn't quite get to 0, so that's some error that's going to be in there. But like, yeah, so this should be, ooh, what happened? That's not right. Because the previous one, I got it right. Like if we go down to the previous one, which is much many more steps. Right there, yeah, I got that to be almost exactly right at 5. How many steps did I go through? Ooh, 956. And how many is in this one? Only 462. Interesting. Okay, so let me go back and change this out. I'm going to delete that. And let's see. How many? Let me open up my other one. All right, so apologies for my non-linear thinking here, but this is the Beard Johnson one. This is the one that I did previously. And what was my what did I do differently in here? 191 animate during simulation. And oh wait, that goes all the way to 5 seconds. Why did I do that? All right, so interesting. I don't know why. All right. Why did I guess I guess I did it to 5 seconds for some reason. I don't remember why. Let me go back to this one. Don't bark. All right. So this one's in meters per second. I want to be in millimeters, right? I want to be in millimeters. Yeah, so that would have changed some of the results, but they shouldn't have been that much different. Let me change this up. Thank you, Layla, for your commentary. You're so ferocious. All right, so this is going really slow. How long is this video right now? 30 minutes. All right, the dogs stopped barking. Let's see. Trying to figure out why this one isn't giving me results. So that's going to be part of the task here, is to try to get results that are comparable to what's in what's in the example or homework problem, I should say, that you're doing right here. But I just want to prove that I can do it, get the right ones. So let me see. Let me change. First off, let me change or double check my angular displacement. I'm going to edit that. That should start off at the right angle, the correct angle. So I think what I need to do is have that. Or let me see. Clear those and have it be this versus that. Is it going to let me do that? Yeah, I think so. Yeah, it's going to start out with a -60 right in there. That's going to help a little bit. And I did change it from millimeters to meters. That's going to be good. Let me see. Let me export it again. Not edit feature. I want to export to spreadsheet. And it'll take a little bit before this pops up. Boom. All right. And let's see. See, it starts at 90. Okay, that's good. I still don't like the fact that it didn't give me the same increments that I had before. Of course, I picked it a longer time. It's weird though that I swear that I had. I don't know. I'm losing my mind. So, yeah. So we want that -90 again. and to see what is the negative 90 right here. This should be when we have, and there you go. Or was this is the angular? Is that the angular? Yeah, that's the angular. That's why. Because let's see, what is the top right here? We had the linear velocity in that's going to be the x direction, and this is the y direction, and that's the velocity, and this is the acceleration. All right. So down here, negative 900. Yeah. Okay. So it's not great. This should be, because we're not exactly at 90, so that's the problem. But this is pretty close to being what we would expect, right? I would like better than that. Negative 935, where it should be negative 900. And come back to this. You could also see this is the y direction should be 0, but it's not right there. But it is very close. See, it's it goes from negative here to positive. So we are crossing 0 right there. It's going from a negative to a positive. So 0 is somewhere in between there if we get the angle right, because it's closer to 91 degrees. And these guys are both going to be in degrees per second and degrees per second squared. Right? So this angular velocity is actually in degrees per second, and the angular acceleration is in degrees per second squared. And the angular velocity, if you'll remember from this problem, is actually 0, right? Because this thing is in pure translation from that example. So if we go to here, we want to compare it. What we do is turn this into radians per second. So let's just use the radians command that turns degrees into radians. Radians, whoops, I didn't put an S in it, that's why. Right there. So you can see that's a pretty small number. And there we go, that's close to 5, right? So this is 5 radians per second squared. That's what this is supposed to be. It's supposed to be, and it's positive, right? So it's supposed to be positive 5 radians per second squared. So we can see that we got pretty close to it. Now what I needed to do was maybe rethink what my time increments were in order to get this amount right here. But I got pretty close in the previous one. Like if I were to go to here, just to prove to you, and because my time, for whatever reason, I made it 5 seconds. I thought for sure that I had made it go to that 2.3875, and I'm not sure. Not sure what the increments were. 191 was the same logic I had used in there. It didn't make sense. But if I go to my results and I pull them out, and no, I guess I got it. No, this is the one I gotta show it first. I show it, and then you can see that I put a bunch more in there and export it to Excel. It'll take a second before it gets there. You can kind of see actually down here, you can kind of see it as it's adding all this stuff to an Excel file. It's kind of funny. There you go. So we take a look here, and I didn't put them in the same order, but here's my angle right here. Here's the angular thing, and I turn it back into just numbers for my scientific. Sure, but look how good those increments came out, right? Of degrees. Why did this one work? You know what? It might have been the angular speed might be different. Maybe Well, I'll take a look at that right there. But if you get down to, where's my, when this thing comes back to 90 degrees, just to show you, so you believe me, when it gets to 90 degrees, right there, boom. The acceleration, one of the accelerations is downright close to being, see which column am I looking for? I'm going to have I think it's this linear acceleration area, so it's going to be column E. You can see it get a lot closer to being the 900, right? Is it supposed to be 900 or 500? 900, yep, it's supposed to be 900, and look how close I got. 900 here. And the same thing for the angular, let's see here. Yeah, you can see, so I'll go radians for this one. That's pretty close to being 0, right? So this is because this is the angular velocity. And you can see it's going from negative to positive right here, so it's just on the verge of being 0. And then this guy right here, he's pretty darn close, right? So video went longer than it needed to. Maybe you can zoom through some of these things, but that's this is a helper to try to get you started for that example problem or that bonus points. Done.